Our world is built on remarkable materials. These materials form the backbone of our infrastructure, shaping the very environment we live in. Among these, one stands out for its versatility and strength. One of the most vital is cement. This seemingly simple substance is the cornerstone of modern construction. This fine powder, when mixed with water, transforms into a binding agent of incredible strength. It undergoes a chemical reaction known as hydration, which allows it to harden and gain strength over time. Cement is the key ingredient in concrete. Concrete, a composite material, is made by combining cement with aggregates like sand, gravel, and crushed stone. From towering skyscrapers to sturdy bridges, concrete shapes our modern landscapes. It is used in a myriad of structures, providing durability and resilience. It provides the foundation for our homes, roads, and infrastructure. Without cement, the development of our cities and towns would be unimaginable. But have you ever wondered how this essential material is made? The process is both intricate and fascinating, involving several stages and a variety of raw materials. The journey from quarry to construction site is a fascinating one. It begins with the extraction of raw materials from the earth. The process begins with raw materials, primarily limestone, a sedimentary rock found in abundance across the globe. Limestone is rich in calcium carbonate, which is essential for cement production. Limestone is the backbone of cement production. It is carefully extracted and transported to the cement plant, where it undergoes further processing. But other materials like clay, shale, and iron ore also play a crucial role. These materials are mined and then combined with limestone to create a mixture that will eventually become cement. These ingredients, each with their own unique properties, are carefully selected and combined to create the final product. The mixture is then heated in a kiln at high temperatures, resulting in the formation of clinker, which is then ground to produce the fine powder we know as cement. Our journey starts in vast quarries where colossal machines extract limestone from the earth. These quarries are like open wounds on the planet's surface, revealing the layers of geological history. Excavators resembling giant metal beasts bite into the rock face, extracting enormous chunks of limestone. Dump trucks, dwarfing even the largest land animals, transport these heavy loads to the processing plant. But limestone is not the only ingredient in this recipe. Clay, shale, and iron ore are also mined and transported to the cement plant. These materials, often found near limestone deposits, contribute specific properties to the final cement product. The extraction process is a testament to human ingenuity and the power of modern machinery. Once the raw materials arrive at the cement plant, the real transformation begins. The first step is to break down these massive rocks into manageable pieces. Imagine the force needed to pulverize a mountain. This is where giant crushers come into play. These mechanical behemoths, some taller than a multi-story building, crush the limestone, clay, shale, and iron ore into smaller fragments. The air vibrates with the sound of rocks grinding against steel. It's a symphony of industrial power. The crushing process happens in stages, with each stage reducing the size of the materials further. The goal is to create a fine powder, essential for the next stage of the journey. Now, the finely ground raw materials embark on a fiery journey. They are fed into a massive rotating kiln, a cylindrical furnace that stretches over 150 meters long. This is where the magic happens. Inside the kiln, temperatures soar to over 1,400 degrees Celsius, hot enough to melt many metals. As the materials heat up, they undergo a series of chemical reactions. This process, called calcination, is the heart of cement production. The intense heat transforms the limestone, clay, shale, and iron ore into a new material, clinker. Clinker, resembling small, dark gray pebbles, is the essential component of cement. Section 5. Clinker formation, the heart of the process. Inside the fiery belly of the kiln, a fascinating transformation takes place. This is where the raw materials undergo a series of complex chemical reactions, driven by the extreme heat generated within the kiln. As the raw materials reach temperatures exceeding 1,400 degrees Celsius, they begin to fuse and react with each other. This high temperature is crucial for breaking down the raw materials and initiating the chemical processes that will eventually form clinker. Limestone, primarily calcium carbonate, decomposes, releasing carbon dioxide and leaving behind calcium oxide. This decomposition is a critical step, as it sets the stage for the subsequent reactions that will form the core components of cement. This calcium oxide then reacts with the other components like silica from clay and alumina from shale to form complex compounds. These reactions are meticulously controlled to ensure the formation of the desired compounds that give cement its strength and durability. The iron oxide, present in small amounts, acts as a flux, lowering the melting point of the mixture and facilitating the chemical reactions. This helps in achieving the right consistency and composition of the clinker. The result of this intense heat and chemical transformation is clinker, a new material with remarkable binding properties. Clinker is essentially the building block of cement, and its formation is a testament to the intricate processes that occur within the kiln. Clinker emerges from the kiln as small, grayish pebbles, ready for the next stage of its transformation. These pebbles are then cooled and ground into a fine powder, which is mixed with gypsum to produce the final product, cement. This cement will go on to form the backbone of countless structures around the world, highlighting the importance of the clinker formation process. Section 6. Cooling and grinding, from clinker to cement powder. After its fiery ordeal, the clinker needs to cool down. It travels on a conveyor belt system, exposed to cool air, gradually reducing its temperature. Once cooled, the clinker is ready for its final transformation. It enters a giant grinding mill, where steel balls pulverize it into a fine powder. This fine powder is what we know as cement. During the grinding process, a small amount of gypsum, about 3 to 5%, is added to the clinker. Gypsum helps regulate the setting time of cement, preventing it from hardening too quickly when mixed with water. Section 7. Ready for action, storage and packaging. The freshly ground cement is now ready for its final destination construction sites around the world. But first, it needs to be stored and packaged properly. Cement is highly sensitive to moisture, so it's crucial to keep it dry. Large airtight silos, often towering over the cement plant, provide the perfect storage solution. From the silos, cement is either transported in bulk carriers or packaged into bags. Bulk carriers, specially designed trucks or train cars, transport large quantities of cement to construction sites. For smaller projects, cement is packaged into bags, typically weighing 50 kilograms each. These bags are then loaded onto trucks and shipped to distributors and retailers. Section 8. The environmental impact challenges and solutions. The cement industry, while vital for our infrastructure, faces environmental challenges. The production process is energy intensive and releases significant amounts of carbon dioxide, a greenhouse gas contributing to climate change. However, the industry is actively seeking solutions to reduce its environmental footprint. One approach is to improve energy efficiency in cement plants. Another is to explore alternative fuels, such as biomass or industrial waste, to replace fossil fuels. Researchers are also developing new types of cement with a lower carbon footprint. These innovations aim to make cement production more sustainable, ensuring a future where our built environment coexists harmoniously with the natural world. Section 9. Looking ahead, innovations in cement production. The cement industry is not standing still. In fact, it is undergoing a significant transformation. Driven by environmental concerns and the need for sustainable solutions, researchers and engineers are constantly innovating. They are exploring new materials, refining production processes, and seeking ways to minimize the carbon footprint of cement. New technologies are emerging, promising to revolutionize cement production and reduce its environmental impact. These advancements are not just theoretical, they are being implemented in real-world settings, showing promising results. One exciting area of research is the development of geopolymer cement. This innovative material has the potential to change the way we think about cement and its environmental impact. Geopolymer cement utilizes industrial byproducts such as fly ash or slag as its main ingredients, reducing the reliance on traditional clinker production. This not only helps in waste management, but also significantly cuts down on carbon emissions. These alternative materials react with alkaline solutions to form a binder with properties comparable to conventional cement. The chemical reactions involved are complex, but result in a durable and sustainable product. This innovation not only reduces carbon emissions but also provides a valuable use for industrial waste materials, promoting a circular economy. By reusing waste, we can create a more sustainable and efficient production cycle. The future of cement is evolving, driven by a commitment to sustainability and innovation. As these new technologies and materials continue to develop, we can look forward to a greener, more sustainable construction industry.